the operators. The oldest one, is the linear crossover. And the principle of linear crossover is very simple. So I'm just going to discuss the principle of the linear crossover operator. Now the concept of linear crossover in real coded GA was proposed by Wright in the year 1991. 1991, I also did not start learning genetic algorithm in 91. I started learning in 95. Now, according to, so this linear crossover, so supposing that we have got two parents, PR1 and PR2, and these two parents are going to participate in crossover. Now, from these two parents, how to get the children solutions? Now, according to the linear crossover, three children solutions will be produced. Now, the first one is nothing but the average of the two parents. That is 0.5 multiplied by PR1 plus PR2. That is the average of the two parents. Now, the second child could be your 1.5 times PR1 minus 0.5 multiplied by PR2. The third child could be minus 0.5 multiplied by PR1 plus 1.5 multiplied by PR2. Now you see, I've got two parents, PR1 and PR2. Now let me take some example. PR1 is 5.85 and PR2 is at 10.67. Now from these two parents, I'll have to find out how many children solutions? Two children solutions, child 1 and child 2. But here I am getting three children solutions. Now out of these three children solutions, the way Wright proposed that linear crossover, so he actually selected the best two out of these three children solutions and considered these two as a valid children solution. This is the way actually the linear crossover operator was implemented in real coded GA, and it was very simple from the implementation point of view, and it gained popularity because this is the first version of the linear crossover. Many people use and got very interesting results using the linear crossover operator, but there is no end of improvement, and this particular linear crossover had a few demerits. Now to overcome that, in the year 1993, another crossover operator that is called the blend crossover, in short that is known as BLX alpha. So that was proposed by Esselman and Schaefer. They are very famous in the field of genetic algorithm. You might have heard about Schaefer's test function. Whenever we propose something new, some new algorithm, non-traditional optimization algorithm, or the modified version of genetic algorithm, we take the help of some test functions to test its performance. Schaefer's actually proposed some test function, and those are known as Schaefer's test function in genetic algorithm. So I'll request you all to go to Google search and you just write down Schaefer's test function in genetic algorithm. You'll be getting the mathematical expression of these particular the test functions. Now, Esselman and Schaefer in the year 1993 proposed the concept of blend crossover. Now, once again, supposing that there are two parents, PR1 and PR2, and they are participating in crossover, and our aim is to determine the two children solution, that is your child 1 CH1, child 2 that is CH2. Now according to this blend crossover, the way child 1 and child 2 was created is as follows. Child 1 is nothing but 1 minus gamma multiplied by PR1 plus gamma multiplied by PR2. So I know PR1 and PR2, parent 1 and parent 2. I'll have to find out what is this particular gamma, which I'm going to define soon. And if I know gamma parent 1 and parent 2, very easily you can find out what is child 1. Similarly, child 2 can be determined as 1 minus gamma multiplied by PR2 plus gamma multiplied by PR1. What is gamma? Gamma is nothing but is your 1 plus 2 alpha multiplied by R minus alpha. And that is why this is BLX alpha. Now this alpha will have some fixed value, say 0.5. So this is popularly known as BLX 0.5 or BLX alpha. Okay, so here I am considering alpha equals to 0.5. Now, if I consider alpha a fixed value and that is equals to 0.5, I have got another random variable that is R. So R is a random number lying between 0 and 1, and that will be actually generated using a random number generator. If I know the value of alpha, if I know the random value of R, very easily I can find out what is gamma. And if I know gamma, then using the information of PR1 and PR2, I can find out child 1 and child 2. Now, after the introduction of blend crossover, it gained popularity and it could overcome some of the demerits of this linear crossover and it became very popular. So it was proposed in the year 1993, then 94, 95. So it could get that particular popularity. Then in the year 1995, another crossover operator was proposed that is known as simulated binary crossover, that is SBX, and that was proposed by Deb and Agarwal in the year 1995. And you'll be astonished to listen, this was the outcome of one MTech thesis at IIT Kanpur. That MTech thesis was done by Ram Bhushan Agarwal. So I also started working for my PhD around 95, 96. So I had some interaction with Agarwal, Ram Bhushan Agarwal, and that was guided by Professor Kullanmoy Deb at IIT Kanpur. Now, so it was developed in the year 1995, and that is popularly known as simulated binary crossover, that is your SBX. Now, let us explain the working principle of these particular SBX crossover operator. Now, in SBX, search power is represented with the help of generated children solution from the given parent. So we have got two parents, we'll have to generate two children. To generate the children solution, we take the help of some polynomial function, so which I'm going to discuss soon. So now before I proceed further, in this particular simulated binary crossover, so I'll have to define one term. That particular term is known as spread factor, that is denoted by alpha. Now, to define this particular spread factor, that is alpha, we take the help of the ratio of the difference between the two children solution to the difference between the two parent solution. So we find out the ratio, and of course we consider the mod value. So I have got two parents, PR1 and PR2. So I know the difference between PR1 and PR2. But actually, there is no such rule that always PR1 has to be greater than PR2. So this particular difference could be either positive or negative. Similarly, there is no hard and fast rule that child 1 will be greater than child 2, and consequently it could be either positive or negative, and we take the help of this mod, that is the positive value. So we try to find out a ratio of the difference between the two children solution to the difference between the two parents. Now there are three possibilities for this particular the spread factor. Now depending on the children's solutions for the known parents, there could be three possibilities or three cases. Case 1, for alpha is less than 1. Now alpha less than 1, what do you mean by that? It means that the difference between the two children is less than the difference between the two parents, and consequently this alpha is less than 1. If alpha is less than 1, that is known as the contracting crossover. So I'll be discussing in much more detail like the concept of this contracting crossover. Now case 2, that is your expanding crossover, where alpha is greater than 1. That means the difference between the two children is more compared to the difference between the two parents, and that is your your expanding crossover, that is alpha is greater than 1. There could be a third case, but generally it doesn't happen, but it may happen, possibility is there. That is called the stationary crossover, where alpha is equals to 1, and that means your the difference between the two children solution is exactly equal to the difference between the two parents. So there could be three cases, either contracting crossover or expanding crossover or stationary crossover. Now I'm just going to show you a plot for this plot of the polynomial function, just to represent the three zones of contracting crossover, expanding crossover, and stationary crossover. But before that, let me repeat, which I've already mentioned, that here we take the help of probability distribution expressed in terms of polynomial function just to create the children solution from the two given parents. Now, how to determine the children solutions from the given parents? Now, before I discuss so this particular plot of the probability distribution of polynomial distribution, now let me first concentrate on the mathematical expression which was proposed for the contracting zone and the expanding zone. Then I'll be coming back to your so this particular plot. Now let us try to concentrate first on the mathematical expression which they used. As I told, they took the help of polynomial distribution. Now remember, this is also not the unique. Many people propose different mathematical expression just to represent this contracting zone, expanding zone. So this particular mathematical expression is not the unique. Now the way they explained is as follows. The contracting crossover C alpha is nothing but 0.5 multiplied by q plus 1 multiplied by alpha raised to the power q. What is q? Q is nothing but a positive real exponent. I think some of you might be knowing that in computer science, there is a trend not to utter this positive. So in place of positive, they always say it is non-negative. In place of positive, they always say non-negative real exponent. So Q is nothing but non-negative real exponent. So Q could be equal to 0, it could be greater than 0, it could be 1, it could be 20, it could be 30, and so on. Okay, and what is alpha? Alpha is nothing but the spread factor which I have already discussed. Now, why did you consider this type of mathematical expression? That I'm going to tell you. But let me first concentrate on the expression for this expanding crossover. The expanding crossover that is denoted by Ex alpha, that is nothing but 0.5 multiplied by q plus 1 multiplied by 1 divided by alpha raised to the power q plus 2. Once again, this mathematical expression is not the unit. If you see the literature, you'll be getting many such expressions. Okay, other type of expression you'll be getting. Now, this is one of the most popular expressions which you use for contracting and expanding crossover. Now, I'm going to discuss why do you consider this type of expression. Now, to investigate that, let me put q equals to 0. Now, if I put q equals to 0, what will happen? This will become 0.5 multiplied by 1. Then alpha raised to the power 0 is once again 1. Okay. So I'll be getting C alpha is a constant value and that is equal to 0.5. So in the contracting zone corresponding to Q equals to 0, I'll be getting one constant value that is 0.5. Now let us see what happens if I put Q equals to 0 in the expression of expanding crossover. If I put Q equals to 0, so this will become 0.5 multiplied by 1 divided by alpha square because Q equals to 0. So this becomes 1 divided by 2 alpha square. So 1 divided by 2 alpha square is the expression for the expanding zone corresponding to Q equals to 0. Now you concentrate on this particular the plot. So this is the plot. The probability distribution or polynomial probability distribution. Now here this is the direction of alpha. So alpha equals to 1.0 is a stationary crossover. Alpha less than 1. So this is nothing but the contracting zone. Alpha greater than 1. This is nothing but the expanding zone. Okay. And corresponding to Q equals to 0 in the contracting zone. So this is 0.5. Okay. And in the expanding zone corresponding to Q equals to 0. So 1 divided by 2 alpha square. So as alpha increases, this particular value is going to be reduced. Are you getting my point? So this is the plot in the expanding zone corresponding to Q is equals to 0. Now, if I take a higher value for this Q, that means I'm taking Q equals to 2. So in the in the contracting zone, so I'll be getting this type of nonlinear distribution. And in the expanding zone, I'll be getting this type of nonlinear, the distribution for the function. Then if I take even a higher value of Q, so Q equals to 10, so I'll be getting a very steeper distribution like this. So this could be the expression or distribution in the contracting zone, and this will be the distribution in the expanding zone. Now, what is the observation? Observation is very important. Now, the observation is as follows. The less the value for this particular Q, the wider will be the range for the distribution and vice versa. That means the higher the value of Q, the steeper will be the distribution. Now, what do you mean by this steeper distribution? By a steeper distribution denoted by the higher value for this particular Q, the children's solutions are bound to be very close to the parents. Are you getting my point? So if I take a very high value for Q, the children's solutions will be closer to the parents and you may not get the required diversification in the children's solution. On the other hand, if you consider a very small value of Q, the children's solutions could be too far from the parents There could be too much diversification, but if there is too much diversification, it may not help the genetic algorithm to reach the globally optimal solution. So what you'll have to do, depending on the nature of the problem, the user will have to make some trial runs to decide what should be the most suitable value for this particular the Q. I hope all of you have understood that if I want that the children's solution should be very close with respect to the parents, so we'll have to go for the higher value for this particular the Q. Now remember one thing, this is nothing but a probability distribution. And as it is a probability distribution, what is the area under this particular probability distribution? For example, if I take Q equals to 2, the area under this particular curve will be equal to 1.0. That is the total probability. Okay, that means your area under the curve in the contracting zone should be equal to 0.5, and area under the curve under the in the contract expanding zone will be equal to 0.5, and sum of 0.5 and 0.5 is nothing but 1.0. This is the way. So this particular probability distribution, polynomial probability distribution, was selected. So this particular selection of the probability, polynomial probability distribution is not haphazard. There is a reason behind this particular selection. But once again, this particular probability distribution is not the unique one. Okay, as I told in the literature, you will be getting some other type of expression for this contracting and expanding zone. But the sum of the two probabilities has to be equal to 1.0. Now, as I told, the area under the curve in the contracting zone is equals to 0.5. That means your integration alpha equals to 0 to 1, C alpha D alpha is equals to 0.5. And in the expanding zone, integration alpha equals to 1 to infinity, Ex alpha D alpha is equals to 0.5. Okay, I hope this is clear to all of you. These are nothing but the area under the probability distribution curve in the contracting zone. This is the area under the probability distribution curve in the expanding zone. I hope I'm clear to all of you, and I'll be solving some numerical example. I'll show you that very easily can find out the children's solution with starting from the parents, and your doubt, if any, will be cleared. But before that, let me concentrate on the steps which we generally follow in this SBX, that is simulated binary crossover. Now, step one, we generate a random number using the random number generator, that is and R, and this R is lying between 0 and 1.0. Step 2, determine alpha prime. What is alpha? Alpha is the spread factor. What is alpha prime? A special value for this particular alpha, for which integration 0 to alpha prime C alpha D alpha becomes equal to R. What is R? R is nothing but the random value generated between 0.0 to 1.0. Now, there are two possibilities. Why two? There are three possibilities, I should say. R could be less than 0.5. R could be exactly equal to 0.5. And R could be greater than 0.5. Now, supposing that R is found to be less than 0.5, say 0.4 or 0.3 or 2. So if it is so, that we can find out integration 0 to alpha prime C alpha D alpha is equals to R, and I can find out this particular integration, and I can determine a particular value for this particular alpha prime, for which the area under this particular curve will be equal to R. Okay, and all of you know this is in the contracting zone, so alpha will become less than 1.0. Now let us see what happens if R becomes exactly equal to 0.5. All of you know if R becomes equal to 0.5, so you'll be getting what is the value of alpha prime? Alpha prime will become equal to exactly equal to 1.0, and that will represent the stationary crossover. Now in the expanding zone, supposing that R is found to be more than 0.5, so 0.7, 0.9 and so on. In that case, integration alpha equals to 1 to alpha prime, Ex alpha d alpha is equals to R minus 0.5. So this Ex alpha is going to represent your expanding crossover zone. So I can find out the alpha prime corresponding to this where R is greater than 0.5, and definitely I'll be getting one alpha prime which is greater than 1.0. I think it is clear to all of you. I'll be taking numerical example. I'll show you. Just wait a little bit. Now once I've got the value for this particular alpha prime, very easily can find out what is child 1 and child 2. Now knowing the value for this particular alpha prime, knowing the values for this PR1 and PR2, how to find what child 1 and child 2, that I'm going to discuss. Now to find out child 1 and child 2, what we consider first the average of the two parents, that is PR1 plus PR2 divided by 2, that is 0.5 multiplied by PR1 plus PR2. Then what we do is we know the value for this alpha prime. So alpha prime multiplied by the mod value of the difference between parent 2 and parent 1. That so the difference between parent 2 and parent 1, its mod value, that is multiplied by alpha prime, that is the spread factor. Okay, and spread factor, you know, the ratio between the difference between the children and the parent, that is multiplied by the difference between the two parents. So consequently I'll be getting the difference between the two children. Now the difference between the two children solution, so we take 50% of the difference between the two children. Okay, although initially we do not know, that is why we take the help of the mathematical expression, that is alpha prime, we know the numerical value, PR2 and PR1, the difference we know, but truly speaking, we do not know till now the difference between the two children. So indirectly, we find out the difference between the two children by following an indirect method. And 50% of this particular difference, we subtract from for getting child 1 and we add for getting child 2. I think I am clear to all of you. So the difference between the two children, which we calculated indirectly using this particular expression alpha prime and the difference between PR2 and PR1. So that particular difference, we take 50% of that particular difference, we subtract it here for getting child 1 and we add it here for getting child 2. So this is the way we calculate child 1 and child 2 starting from the two parents. So using this SBX, very easily you can find out the children's solutions. Now to clear your doubt, if you have any, I'm going to take the help of one numerical example. The way I have designed this numerical example is very simple. So we'll have to use SBX just to find out the children's solutions of the two parents, that is PR1 and PR2. PR1 is 20.65 and PR2 is 15.50. I'm going to use SBX, and the value of Q I take that is equal to 3. So the value of the exponent q that is taken equal to your 3. Now let us consider that my random number generator has generated a number that is your 0.4, that is less than 0.5. As it is less than 0.5, we calculate alpha prime using this particular expression, that is integration 0 to alpha prime C alpha d alpha, that is equals to R. R is nothing but 0.4. Now if you carry out this particular integration and if you simplify and then you'll be getting the value for this particular alpha prime. Here q is equals to 3 and R is 0.4. So very easily you can find out the unknown, that is your alpha prime. And if you solve, so this is the integration, and if you further solve it, then you'll be getting alpha prime equals to 0.94, and that is less than 1. It is obvious because this is in the contracting zone. So once you've got this particular alpha prime, very easily you can calculate the children's solution. That is child 1 is 0.5 multiplied by PR1 plus PR2 minus alpha prime into PR2 minus PR1, their mod value, and alpha prime is 0.94. If you substitute all the numerical values, you'll be getting 15.66. So this is your child 1. Similarly, you can find out child 2 and you'll be getting 20.50 as child 2. So we have got two children, that is child 1 is 15.66 and child 2 is 20.50, starting from the two parents, that is PR1 is 15.50 and PR2 is 20.65. Now you see, the difference between the two parents is this much and the difference between the two children's solution is this much. And here alpha prime is 0.94. That means it is in the contracting zone. So the difference between the two children's solution will be less compared to the difference between the two parents. So this particular solution is correct. So this is the way actually using the SPX operator, you can find out the two children solution starting from the two parents. I think I'm very much clear. Okay, but if there is any doubt, definitely I'm going to listen to you at the end. Let me finish it fast. Now I'm just going to use mutation operator. So using the mutation operator, so how to modify the solution so that it can come out of the local minima problem. Now, if you see the literature, a number of mutation operators had been proposed for this real coded GA. Out of all the proposals, the most popular one is the random mutation and another polynomial mutation, which I'm going to discuss. Now, according to this random mutation, the mutated solution, that is PR mutated, parent mutated, is nothing but PR original plus R minus 0.5 multiplied by delta. What is R? R is a random number lying between 0 and 1. What is delta? That is the maximum value of perturbation. All of you know the meaning of this particular term, perturbation. Perturbation means dissimilarity. That means whenever we are going to find out the mutated solution, how much dissimilarity you are going to allow, okay, in the mutated solution in comparison to the original solution. That is decided by your this delta, that is your maximum value for this perturbation or maximum value for this particular dissimilarity. How to find out? How to assign a suitable numerical value? It is very simple. It depends on the range for the variable. Let me take a very hypothetical example. Supposing that the range for a variable is 0 to 1 and another variable, the range is 1 to 100. So if the range is 0 to 1, the value of this particular maximum perturbation will be much less compared to when the range for this is lying between 1 and 100. Let me repeat. The range for x1, the first variable, is lying between 0 and 1. The range for the second variable is lying between 1 and 100. Now, this maximum value of perturbation for the first variable x1 and the maximum value of perturbation for the second variable x2 will not become equal. Definitely for the second variable, the value of this maximum perturbation, that is delta, will be much higher compared to that for the first variable. I think I'm clear to all of you. Now I'm just going to concentrate on this polynomial mutation, which is very popular. Now, once again, we take the help of some polynomial distribution, and how to select that particular polynomial distribution I'm going to discuss. And once again, you'll see the expression for this polynomial distribution is not the unique. Now, let me concentrate on the steps which we generally follow in polynomial mutation. Step 1, we generate a random number r lying between 0 and 1, and supposing that we have got the value for this particular r. Say r could be less than 0.5, r could be exactly equals to 0.5, or it could be greater than 0.5. These are the possibilities. Now I'm trying to find out one factor that is called the perturbation factor, that is delta bar. What is delta bar? Delta bar is defined as 2r raised to the power 1 divided by q plus 1 minus 1 if r is found to be less than 0.5, and if r is found to be greater than equals to 0.5, so delta bar is nothing but 1 minus 2 into 1 minus r raised to the power 1 divided by q plus 1. Now, my question is, why do you select this type of expression? And as I have told, the selection of this particular expression is not the unique. If you see the literature, you'll be getting some other expression. But this particular expression, the way it was selected, it has got one philosophy. It has got one reason. What is that particular reason? To understand that particular reason, what you do is you put r equals to 0. R is less than equals to what? 0.5. Put r equals to 0. And supposing that q equals to 10. So if I put r equals to 0, so this will become delta bar will become minus 1. And if I put r equals to 1, what will happen? If I put r equals to 1 here, extreme, I'm considering two extreme values for this particular r, that is 0.0 and 1.0. So if I put r equals to 1.0, so I'll be getting delta bar is nothing but 1. Now you see the real beauty of this particular, the selection. Delta bar is lying between -1 to +1 in the normalized scale. You know, the normalized scale could be either from 0 to 1 or from -1 to +1. I'll be discussing all such things in much more detail whenever I'll be discussing the concept of neural networks. Okay. Now, for the time being, let me concentrate on the fact that delta bar lies between -1 to +1, and so this particular delta bar is going to help us to find out what should be the mutated solution if I know the original solution. Now this PR mutated is nothing but the PR original plus delta bar is a perturbation factor multiplied by delta max. What is delta max? That is the maximum user defined maximum perturbation value. That means how much dissimilarity you are going to tolerate in the value of the variable due to this particular your mutation. Let me take a very simple example. How to decide the suitable value for this particular the delta max. Let me once again take one example. Supposing that for the first variable x1, the range is 0 to 1. The second variable, the range is 1 to 1000. So for the first variable, range is 0 to 1.0. The second variable, the range is 1.0 to 1000.0. So the delta max for the first variable and delta max for the second variable, they cannot be the same. Now let me put some hypothetical value. For the first design variable, delta max could be 0.02, where the range is 0 to 1. For the second variable, delta max could be 5.0, where the range is lying between 1.0 to 1000.0. Okay, so this selection of delta max, it depends on the range for the variable. Now remember one thing, delta max cannot be too less, it cannot be too large. What is the reason? If it is too less, the very purpose of using delta or the mutation will not be served. If it is too large, the search will become a random search. But GA is not a random search, as I told several times. This is some sort of controlled random search. Okay, so we'll have to select this particular delta max very carefully. Now I am going to solve one numerical example just to make it crystal clear. Now supposing that the original parent is 20.85, our aim is to determine the mutated solution and we consider R equals to 0.6, Q equals to 4 and delta max I am considering for simplicity say 1.5. How to find out your mutated solution? Now here I'll have to use this particular expression because R is found to be greater than 0.5. So delta bar, that is the perturbation factor, is nothing but 1 minus 2 into 1 minus R raised to the power 1 divided by Q plus 1. Q equals to 4 here, R equals to 0.6, and if you simplify, you'll be getting delta bar equals to 0.04. And once you've got, so this particular perturbation factor, very easily can find out the mutated solution. Now this PR mutated is nothing but PR original plus delta bar multiplied by delta max, and if you just insert the numerical values, so you'll be getting PR mutated is 20.91, our original solution is your 20.85. So there is a little bit of change in the mutated value of this particular variable using the polynomial mutation. I hope the principle of this real coded GA is clear to all of you. This is the working principle of the real coded GA. Now, before I conclude and before I give you the opportunity to interact with me, let me tell you one fact. This real coded GA was implemented to solve a variety of problems. People were very happy, but this particular real coded GA has got one demerit, and that is nothing but there is no concrete convergence mathematical proof, not even an indirect proof like schema theorem, which we have for the binary coded GA. So for this real coded GA does not have any direct mathematical convergence proof till date, and it does not have even indirect mathematical proof for convergence, which you have for the binary coded GA like schema theorem. So the schema theorem is not valid for this particular, the real coded GA. So there was a lot of criticism of this particular, the real coded GA. But my personal experience says that we could solve a number of optimization problems using this real coded GA very efficiently. Now I'll give you the opportunity, like if you have any doubt, so I'll try my level best to clear your doubt. So if you have doubt, you can ask me one after another. Okay, so now it is open to discussion.
Sir,
Please.
sir, can you once tell about the maximum value of perturbation in the random mutation?
The maximum value of perturbation in the random mutation, that value depends on the range of the design variables. Okay. If you have a very narrow range for the design variable, so you'll have to assign a small value for this perturbation. On the other hand, if you have very wide range for the design variable, you can even go for a higher value for this particular, the perturbation. I think I am clear. Next.
Yes, sir.
Yes.
Hello, sir.
Tell me.
Sir, am I audible?
Yeah.
Yes, sir. Sir, in the slide 43, sir, in the blend crossover.
Blend crossover. Okay, let me go back. Blend crossover. Okay, tell me the problem. Tell me the problem. Please tell me the problem.
Mic got muted. Yes, sir.
Just
Gamma
a
is a
minute.
weight. Yes, sir.
Gamma. Blend crossover. Yes. Tell me.
Yes,
gamma
sir.
is.
Gamma. Yes, sir. Gamma is a weightage value, acting like a weightage value, right, between parent 1 and parent 2.
Exactly. Exactly.
Yes.
You are right.
Yes, sir. It has a value of 0 to 1, means it should have a value of 0 to 1.
Actually, the way actually Esselman and Schaefer, they calculated, they took the help of this particular expression. Okay. Now, the moment I put 1 minus gamma, and this is gamma. Okay. So what does it mean? If you just add them up, this weighting factor, this is equal to 1.0. Are you getting my point? See, the weighting factor, for example, say 1 minus gamma is 0.3. The gamma has to be 0.7. So we put 30% weightage to parent 1 and 70% weightage to parent. It is actually how to, whether I'm going to give more weightage to parent 1 or more weightage to the parent 2. Okay. Accordingly, children's solution will be either closer to parent 1 or parent 2. Okay. Generally, we consider the difference. We always consider the difference. We do not compare child 1, parent 1, that type of thing. We always try to concentrate on the difference. Okay.
Yes, sir.
Okay.
Sir, I was means my follow-up question was, and since gamma is dependent on the random variable r, which varies from 0 to 1, why can't we take the random variable in place of gamma? Like,
yes,
I
can take, there is no problem. But here, there is one control of alpha. Okay. Alpha actually, depending on the problem, the user may supply the value for alpha. For example, alpha equals to 0.5, alpha equals to 0.6, alpha equals to 0.4. So the user can make some trial and error run just to decide the value for this particular alpha, so that this particular crossover operator becomes more efficient to solve a particular problem, and that is problem dependent. So that particular flexibility is given in this particular algorithm. If you directly use R, so that particular flexibility will be lost. Okay.
Yes, sir.
Hmm.
Yes, sir. So we are making it a more controlled rather than being more
Yeah,
random.
yeah, exactly. That is why no, in
Okay,
genetic
sir. Okay.
algorithm, it is a
Sir, I had. Yes, sir.
random, controlled random, sir.
Yes, sir.
Hmm.
Yes, sir. Yes, sir.
Hmm.
Sir, another question, sir. In slide 48, sir.
Right.
That's in.
Related to, just
Sir,
a minute,
this is related to Q, sir.
just a minute.
Uh,
48, yes.
yes, sir.
Yes. Hmm.
In this, we obtained that when Q is high, then
Hmm.
diversification is very less, and
Yeah,
when Q is very low,
yeah,
diversification is too much and solution is slower.
okay.
And
Ah,
therefore we have to choose an optimum like optimum Q to obtain a according to the problem.
okay.
And therefore my question is, why should we take any optimum? Because
You
if Q
see,
is higher, then
hmm,
solution will be faster
solution will
and
be
we will
faster.
get the result.
Solution will be faster, but there will be a chance of premature convergence. I'm declaring I'm the best in the field in the world, but I'm truly speaking not the best. That is a clear example of premature convergence. Are you getting my point? If I take a higher value for this Q, I will have premature convergence. Are you getting my point? I'll think I'm the
Yes, sir.
best in the world, but truly speaking, I'm not because there is no end of learning. Okay. So if I take Q equals to very high, diversification will be lost and genetic algorithm will be giving you one optimal solution that may not be globally optimal. That
Yes,
guarantee
sir.
is not there at all. So what you'll have to do, you see, I'll have to keep a proper balance, if you remember, of the selection pressure and population diversity. Both the things are to be there. Are you getting my point?
Yes, sir.
So I should be known for a few subjects. Okay. If
Yes,
I want to proceed in my career instead of only one very narrow subject. Are you getting my point? We'll have to be
yes,
very careful. If I want to survive for a long time in the field of teaching or research, okay, I'll
yes,
have
sir.
a very good diversification at the same time, selection pressure also. Same is true for GA. Same
Okay.
is true for GA. Okay,
Sir.
are you getting my point?
Yes, sir. Yes,
I
sir.
think you got my point.
Yes, sir. Yes, sir. Thank you,
Hmm.
sir.
Any other query? Any other query? Okay. So if there is no other query, let me stop here today. Uh,
Excuse me, sir.
yeah, tell me,
Sir,
tell me.
sir, I am not able to buy your book online. So, sir, can you suggest some other book for this first topic, GA? Because it's getting a
GA, you
bit
can
difficult.
see, GA, you can see the book by your David Goldberg, but the topic which I'm going to cover, all the topics are not available in David Goldberg's book also. So please allow me to state. So in my textbook, you'll be getting a more balanced uh, your discussion on genetic algorithm. For example, in David Goldberg's book, real coded GA is not there. Then your a few GA, which version of GA which was proposed by me and others, okay, which are not included in that particular book. So I'm helpless. In fact, you'll have to depend on my PPTs, lecture videos, or there is another possibility. You can see my NPTEL lectures which are available on YouTube for the course traditional and non-traditional tools for optimization. Okay, and there you'll be getting your even the transcript of my lecture is also available. But transcript has not been corrected 100% by me. So I'm still working whenever I'm getting time. But you can listen to that particular video lecture and the video lecture which I'm just putting on the tray of Microsoft Teams. Okay. And you can see the uncorrected and some corrected proofs of my NPTEL course on traditional and non-traditional optimization tools, which are available in your YouTube. You can search like traditional and non-traditional tools for optimization by DQ Prithia. You'll be getting all such lecture videos. Okay. I'm helpless. Or you can do one thing. You can directly give order to the publisher from their site, Narosa publisher site. Okay. Or I think the book was available to your online shopping. Amazon, Amazon it is available. Okay. So I think Amazon it is available.
No, sir. Currently, it is not available on
So
Amazon.
if
But
it is not available, you just write to Narosa with a copy to me. I'll try to find out. Okay.
Sir,
Okay. Yes. Tell me.
sir, videos on the Microsoft Tray are only read only, sir. So we are not able to download it, sir. Can you help us?
No,
download
I
it?
cannot help. That might be, I think, the conditions put by Microsoft Teams. Okay. So there I cannot help you. Okay. You can, I think you can read only, is it?
Yes, sir. Because every time we need internet connection, and I am living in an area which has poor internet
I
connection.
can understand the problem, but it becomes also very difficult for me because, I have so many subjects.
Yes, sir.
So I have so many other things. So,
But in other subjects, sir, we are able to download it, sir.
no, but if that is the problem, then there might be some problem with the Microsoft Teams. That problem I cannot solve. So far as I know, that you participants, the students, will not be able to modify anything. So far as I know. Okay, but you'll be able to view. Okay.
Yes.
I'm helpless actually. If that is the rules and regulations of Microsoft Teams, so I'm also helpless. Okay.
Excuse me, sir.
Please.
Sir, I after registration also I'm unable. I'm not. I haven't received the ERP mail for second assignment, sir. Can you please help in that?
Assignment 2 I've already put on the tray. Okay.
Yes, sir. But that requirements and suggestion you have listed.
It is bit difficult for me individually. If you tell to send, it is bit difficult. So I'll request your other friends to send you. Okay. So you do one thing. All the friends are online now. You tell your email address. Okay. And I think some of your friends have knowledge base. I think you belong to knowledge base or soft computing.
It's a knowledge based.
Okay. So some of your friends, you are from which department?
Sir, RCG SIDM.
Okay. So there might be some other friends or friends from other departments for the same course. Please take the help of. There is very difficult for me to send.
Sir, I understand, sir. But sir, for this test, it will be like how I will manage.
Test.
Because
You see, I'm telling you one thing. Those who are not registering through ERP, I do not know how to tackle their problem because I found ERP is the most authentic like site through which I should send that particular question paper. I'm going to follow that ERP route only. Okay, for the question paper. Okay, so if that is a problem, you talk to your guide, you talk to your department to kindly solve this particular problem. I cannot solve as a teacher. Okay,
excuse me, sir.
I'll have to believe one source and I'll sending this question paper, and I'll be sending through ERP mail. Although I'll be putting in Microsoft Teams the
yes,
question
sir, that
paper.
I received. That I have received.
I'll put question paper also Microsoft Teams, but I'll be sending through our ERP mail. And another thing, it is clear, it should be made clear. Whoever registers through ERP, they only be getting the grades. Others will not be getting any grade. Be careful about that. Okay? Because I'll have to rely on our ERP registration. Okay?
Excuse me, sir. Can we leave the meeting? We have
Please. You are free.
Sir.
Okay, let me stop here today. Tomorrow we'll discuss. Okay.